name is Jeff, and I'm coming to you live from Rockville, Maryland, which I wouldn't blame you if you'd never heard of, but it's right near Washington, D.C., which you probably have heard of. I worked for NASA for 5 years, and I still work for NASA kind of less formally. I worked on a lot of different stuff, like designing space missions, designing, that's robotic and human, working on nuclear power systems for space exploration, working on new kinds of propulsion and life support and stuff like that. So when I saw the posting for this session, I thought, well, I think I can actually offer a lot of information to these people. So that's me. Where are you all located?
Alaska.
Alaska.
Yes.
Wow. Okay, that's pretty far. Wow. Okay. So great. We can so there was a list of questions that was in the invite, sort of, and we can talk about those, or we can just answer questions, whatever you want.
Why would going to space help us as people?
So I think that the best way to answer that is to say that human beings are explorers. I think first and foremost. Every culture throughout history, everywhere in the world, has done some kind of exploring, whether it was of their local region or the rest of the world or outer space. And in doing that exploring, new resources are found, new people are met, and there's conflict sometimes. But ultimately, it seems to be part of our nature, and it's something that all human beings are drawn to do. Now, that's a pretty philosophical answer. A more near-term answer is that when you go to space, you have to develop a whole lot of really advanced technology to do that. And that technology becomes part of everyday life. So if you look at space exploration, the first technology you needed was rockets, obviously, and those came from World War II. But pretty much as soon as possible after that, rockets were used to develop and deploy a set of communication satellites that completely changed the world forever. And so the thing about space exploration, and the hard part about selling it to people, so to speak, is that it's not always obvious what you're going to get from it. For example, if any of you know anyone who's ever had kidney dialysis, kidney dialysis was invented because of a gasket that was designed for the Apollo moon rocket. It was a fuel gasket, and it turned out to have the membrane-like property that allows blood to pass through while impurities do not pass through. So that's just one of thousands of examples of technologies that came out of the space program. And I think the bigger picture there is that when you set yourself incredibly ambitious goals, like sending people to the moon and not killing them, you have to be so creative with your technology that you end up creating all kinds of things you never would have done if you had tried to do them in the first place. For example, if we send people to Mars, the amount of technology, both in medical and other areas, that will be required to do that is so massive that no matter what it costs, I think we're almost guaranteed to produce much more than that in value for society in the technologies alone, let alone the incredible accomplishment it would be. So that's my answer to that question.
What kind of power does it take to get to space?
Great question. So one of the questions on the website was basically about propulsion systems. And so there's really a couple of ways to think about power. If you look in a physics book, power is defined by the ability to do work. Well, what is work? Typically, it means moving something. If you look in an electrical engineering book or an electrician's textbook, power is the ability to move electricity around. So you really need both. You need to move a big, heavy thing, and you need it electrically powered. So let's talk about both. The basic way a rocket works is exactly the same way that a skateboard works. If you stand on a skateboard and you put your foot down and push, you push this way, and the skateboard goes this way, okay? Right? That's because of something called Newton's second law, which says that if you push in one direction, there's an equal and opposite action in the other direction. You see this all the time. If you lean against a wall the reason you don't fall through the wall is because the wall is hard enough to push back. So there's a slight difference in configuration when you use a rocket, but it's basically the same idea. You have a rocket engine. You have some kind of chemistry happening in here. In most cases, it's the combustion of hydrogen and oxygen. And you have a bunch of combustion particles coming out, and each one of them weighs something. They weigh very little, but there's billions of them. And so by pushing back, there's an equal and opposite reaction going forward. And that is how a rocket moves. Now, it usually moves up, but you get the idea. So basically, you take a bunch of fuel and you blow it up, and you get pushed in the opposite direction to the direction of the explosion. So that's propulsive power. Now, to do this safely, you need all kinds of computers and other equipment to manage everything, which requires electrical power, and that's much less exciting. It just uses batteries. So those are the two kinds of power. Now, actually, you know what? I can be even more clever. You also need political power, or at least financial power, because in order to put anything in space, it's a pretty major step. If you're the government, you need to spend government money on it, or if you're a private citizen or a business, you need a lot of money to do it. So I think that it's important to keep that in mind too.
And just so you know, Isaac Newton is one of my lifelong heroes. And these kids have been exposed to Isaac Newton. So
He should be everyone's hero.
Yes, amen.
There's a great story about him, actually. Apparently he was really absent-minded, and there's a story where someone came to visit him in his lab, and he walks into his lab, into this like waiting room, and Isaac Newton's lunch is on a table there. And someone had brought him his lunch, and he didn't eat it. And then the guest was waiting and waiting. He waited for like 3 hours. He got so hungry he ate Isaac Newton's lunch. And apparently Isaac Newton finally came out to meet the guy, and he said, "Oh, I thought I hadn't eaten my lunch yet, but I guess I did." So I can tell you this is pretty similar to how a lot of space people function.
Can we launch someone to space without using rockets?
That's a great question, and that's something I'm very interested in because rockets really suck. They're really expensive, they're really dangerous, they're really hard to build, they're really hard to control, and I don't think we're ever going to make space access a routine thing, a normal thing like driving down the street until we move away from chemical rockets. Now, the reason we use chemical rockets is because of World War II, in which a bunch of people, after using them to kill people, realized, hey, if we just point this thing in a different direction, we can go all the way up to space. And by the way, if you look at history, there's a theme of incredible technology advancements coming after major military conflicts. So that's why we use rockets today. Now, fundamentally, what you're doing with a rocket is applying energy over a certain amount of time. So if here's the surface of the Earth, and you want to orbit the Earth, meaning if you go straight up, you'll just fall back, right? So you actually need to kind of go like this. And that means you have to put out a huge amount of energy. That's weird. Oh, never mind. I'm looking at it backwards. Okay. You have to put out a huge amount of energy as your rocket moves along this pathway. Some of the ways that people have come up with, other than a rocket starting on the ground, is imagine if you use a balloon and that balloon picks up a rocket and the balloon goes up pretty high and then the rocket launches from a higher altitude. So some people have thought of that. That has some problems because balloons can pick up a lot of stuff, but it'd be a very large balloon to replace a decent sized rocket. There've also been crazier ideas, like there's something called a railgun, which you might have heard of. It's kind of a science fiction thing, although I think there's actually a Navy ship with one this year or next year. But basically, now remember, this is the surface of the Earth. If you built a ramp long enough, you could use a technology called electromagnetic acceleration, which is basically that if you take two rails and you run an electric current through them, a very, very, very large electric current through them, one thing that happens when an electric current flows is a magnetic field is generated. You'll get to that in physics someday. But basically, if you run enough power through a conductor, you'll get a magnetic field that can push in a certain direction. So you can imagine building a couple of these things next to each other, powering them up, and launching something all the way into space. And no one's ever done that, but in principle, it could be done. Now, it turns out that one of the differences between science and engineering is that scientifically, sure, you can do this. Engineering is actually about building things that work, and there's a lot of problems with doing that. That basically, you can't. No one's ever come up with a way to build something like that big enough. Excuse me, without it melting or flying apart or whatever. So that may not work. Another thing people have thought of is a catapult. Imagine if you, imagine if you take, let's see, the best example is the catapult. Let's say I think it's something like if you take a catapult that's as tall as the as tall as the Grand Canyon. Okay. So suppose here's the Grand Canyon, and you're like looking down it. Okay, so this is like you're standing at the bottom of it. If you take some kind of very large, strong, elastic material, string it across, and then you like pull it all the way down, and you put a cantaloupe here or a watermelon. You can get the watermelon about 10 miles into the sky. Now, this also has some pretty significant engineering problems, as you might guess. But in theory, if you built something tall enough, you could launch into space with what is essentially tension instead of chemical energy. The bigger picture here is that it takes the same amount of energy to overcome Earth's gravity, whether that energy comes from chemistry, from tension, or from electricity. And if you've talked about potential versus kinetic energy, have you talked about that? Yeah. Okay. So you need the same amount of kinetic energy to get to space, regardless of where it comes from. It turns out that rockets are still the best way, because all this other stuff is much harder to build. But there's another way that I'm interested in, actually. And if I'm successful in the next few years, you may hear about it from someone other than myself, which is to use giant freaking lasers. So imagine you have a platform, like a launch platform, and you have your rocket here, but instead of a normal rocket, it's got a gigantic chunk of fuel. So this entire thing is fuel. And here you have a giant laser. The function of this laser is to shine very high energy light and ignite this fuel, so it pushes down. So it's still it still looks kind of like a rocket, but instead of having to bring the fuel and the oxidizer, because remember that fuel combustion requires oxygen. This is a normal rocket, fuel and oxidizer, and then they mix and explode. But here, in principle, if you could build a laser accurate enough, you could do something a lot more efficient than chemistry. Now, it's the same amount of kinetic energy you need to get out of the Earth to get into space, but that might be possible. So I'm trying to get something started in that area. So that's your, I think, kind of quick summary of all of the different ways you could, in theory, get into space. But so far, chemical rockets are the best.
Jeff, that's fascinating. How did you come up with your idea? Was it an epiphany? Was it something you've been working on?
So that's not actually my idea.
Okay.
But I was acquainted with the professor who was working on that. What I found, kind of in a broader sense, is one of what the strength that I bring is putting different people's ideas together, sometimes my own ideas, and communicating them very clearly. That's actually my strength. I'm not the lab guy, but I can see the potential in an idea and put the pieces together and make a very persuasive argument for it. That's been very helpful in terms of actual proposal writing for government funding. And so this actually gets to a bigger picture of, like, if you want to be involved in this world in your career, your life, how do you find what you're good at? And most people go to college to do one kind of field or another. They very rarely end up doing that for their whole life. For me, it took me 2 or 3 years to realize that my strength is actually bringing people together and getting ideas, refining ideas. So if anyone is interested in the career side of this, we can also talk about that. But that's sort of you just happened to give me the chance to mention that when you asked that question.
One of the things that I try to reiterate many times to the kids is the fact that they're each going to have their own dreams. They're each going to be have their own heart for something, a passion for something, and as they go finding that passion and how it's going to fit into the cog of life, the wheel of life with the cogs.
I think that's the most important thing that you could do in your teens and your 20s, actually, is figure out what you love so much to do that you would do it for free all day, every day. And for me, that's space, and I get to do it. And so I really think that's the most important thing you could do. And the great thing is, as a student, you can figure it out. You have to be exposed to all kinds of stuff and figure it out. Because when you so I'm 34. Most of my friends, they've either found the careers that they love and they feel really rewarded, or they're miserable because they never did, or they thought they should just make as much money as they can. So I can tell you from the future, find something you love. That's really.
How long does it take to prepare for a space mission?
That's a great question. It depends on what the mission is. There's really two categories, human and not human. So if you're sending a robot up, it takes 10 years probably to send a major mission up to, let's say, to one of the outer planets. 10 years of design and testing and engineering and more testing and engineering until you eventually get to a place where you're almost positive what you built is going to work. On a smaller scale, if you're not going to the outer planets, if you're staying in Earth orbit, probably 3 to 5 years. This is through NASA. If you're a company and you're launching satellites, let's say for communications or other reasons, it could be as little as 1 year because you've built the thing many times, and you know how to build it and you know how to test it, and you have you're just repeating the same thing. So it really varies. Now on the human side, there is no such thing as a routine human space mission, and they're all different. Most recently, they've all been to the space station, and it still takes. So it's kind of hard to answer because certain activities on the space station take years of training to do. Some take less, like if you're not doing science up there, if you're more just keeping the thing working, you're still training for years on the ground of how the space station works. So everything you see an astronaut do in space has been rehearsed and practiced for years. I guess that's maybe the shortest version of the answer. That's why it looks so effortless and why there's relatively few major problems. Imagine if you couldn't move into a house until you spent a year studying the heater.
So they built the space station and they planned it for obviously so it would potentially never fail. So shouldn't they have it set up so people don't have to run it?
Ideally, yes. But the space station, the International Space Station is the most complicated thing human beings have ever built. And it was built by thousands of people speaking many different languages, using 25 different versions of Microsoft PowerPoint, probably. And all with different training and all with different backgrounds. And it is an absolute miracle. Actually, that's not the right word, because it implies it was not a product of hard work. It is an absolute wonder of the world that human beings came together to build it. But because of that, it's extremely complicated. And one of the ways of reducing the risk of operating something like that is to have a lot of maintenance. And the reason for that is a single major failure will kill between 6 and 12 people, destroy $200 billion worth of equipment, and set back the world space effort by 50 years. So that's why it takes so much time and work to maintain.
How do astronauts know when to sleep in space?
Sure. So it turns out that you still get tired after about the same amount of time being awake in space. It can be confusing because you have a sunrise and a sunset every 90 minutes. This is in Earth orbit at the space station. You do see the Earth the whole time, which has got to be some kind of psychological grounding. Now, at the only places people have ever gone are Earth orbit or the Moon. The Moon missions were obviously very unique and very few in number. It took 3 days to get to the moon. And when the astronauts are asked, they said they kind of dozed. They were so excited and scared, they didn't really sleep. But then they were on the moon for, I think, 7 or 8 days. Buzz Aldrin said that he didn't sleep. He didn't actually sleep at all the entire time he was off the Earth. He kind of dozed. Apparently, Neil Armstrong, who, by the way, is just an amazing human being in many different ways, he was totally chill. He slept, no problem. So those are really the extraordinary space efforts. Not that anything is routine, but when you're on the space station, you basically strap yourself into a sleeping bag, Velcro yourself to the wall or the ceiling or the floor because there's no up and down, and you try to sleep. And there's scheduled sleeping times, and that's actually lined up more for the convenience of the mission control than for the astronauts. Because on the ground at Texas, you still have to. There's still a sort of a work day. Now, of course, there's people there 24/7, but because everyone has to sleep anyway, the astronauts generally stick with Central Standard Time. There was one other thing I wanted to add. And this is not really related to your question, I just think it's really interesting. So there's a part of your brain called the amygdala, AMYGDALA, that is responsible for things like fear and anxiety and self-preservation. And they've started recently doing studies of this guy named Alex something, who's a mountain climber. And he can go climb a mountain by himself in the rain with no safety equipment. He doesn't get scared. And they looked into his brain, and it turns out his amygdala barely works. He actually does not experience fear. It's not that he's conditioned himself. His brain does not experience fear. And I wonder if Neil Armstrong is one of those people, because the things he went through, even before he came anywhere near a spaceship, it's just amazing. So I just find that really interesting, because it's only so much you can do with your own mind. You have your own hardware, and you can work on it, and you can work on your own hardware and software in your brain, but nobody with a normal amygdala is going to function like that. So I just think it's interesting and worth keeping in mind for I don't know, general dealing with people. Next question, Batman.
Could you possibly turn off the amygdala?
Well, there's some research that's showing that with different wavelengths of light being transmitted through the skin, you can actually activate and deactivate cells. So, but cells are not nearly as complicated as a whole brain organ. So I'm sure that there's potential for various psychiatric treatments there, but I'd be afraid they'd be more like electroshock therapy than something precise, for a long time. But who knows? But the cells are definitely, even cells in your body that never ever see light unless you're in an operating table, they are optically sensitive. So that's a whole field of itself. I don't know much. Actually, I know a guy who works in it, but I don't know that much about it. But if you're wondering, could you wear a helmet like that turns off your amygdala so you don't get afraid during a space flight? Maybe. So I'm just going to tell you how people go to the bathroom in space because you're all too embarrassed to ask. So basically, there's 2 space toilets on the space station, one in the US side, one in the Russian side. Guess which one you probably want to be using if you have the choice.
US?
Yeah. So there's basically gender-specific attachments to the toilet that I will leave to your imagination, but it is somewhat more comfortable, I'm told. It is somewhat more comfortable than like a porta potty, but it's obviously more like being at home. So the body does not really change its digestive system much in space, unlike other systems which do change. So it's a really big deal, and apparently, like last year, I think the Russian space toilet was broken for a while, and that's a real problem. I mean, 6 people create a lot of waste. So it's kind of funny and silly, but it's a serious problem for human spaceflight. So, yeah. Oh, and in spacesuits, they wear diapers. Yeah. Yeah, it's really not that glamorous. It's really not that glamorous. In fact, the moonwalkers, they basically said that they decided they were just going to eat as little food as possible during their during their moon missions. Now, they weren't very. They all said they didn't get very hungry because they were so excited and scared. But in this majestic moment of human history, to be wearing a diaper, I would probably eat as little as possible too. Now, there was recently a NASA effort called the Space Poop Challenge. It was on the news, and it was inviting people to propose sanitation systems for spacesuits. And they got like 50,000 entries, so lots and lots of people were thinking. I also put in a proposal with a friend of mine, and what we proposed, which I thought was pretty clever, was it was basically like a waste treatment facility inside your spacesuit. So like in the size of a 3-wing binder, it would have basically the abilities of a municipal waste treatment plant. What was a better idea and ended up getting some kind of award, I don't know if they're going to get research funding or not, but basically if you imagine a spacesuit with an opening at the crotch where a tube can come out, a tube can actually like extend, and the waste can come out there. So, it's not glamorous, but it's pretty fundamental to human activity. Sure. And as for showering, you basically sponge bath. And water in microgravity, water doesn't flow exactly. It's sort of like bubble, it beads. It just sort of forms a sphere because of surface tension. So you kind of like grab a sphere of water and like smash it, like press it against your skin, and it kind of expands. If you look it up on YouTube, it's really interesting because it's so alien to what we experience all the time. But apparently the space station smells really bad. Like it just smells like a locker room.
Oh God.
And there's just not a lot of good solutions for that. So there's a lot of work to be done in making human space travel, routine.
So just out of curiosity, do you think we will ever reach more galaxies than our own?
Galaxies, no. Galaxies probably not. Stars, yes. So so here's the sun. Here's Earth. It's about 100 million miles. Oops, I missed a zero.
Oh my. Oh God.
Okay.
I think that's
There you go.
The moon is Earth moon. The moon is 250,000 miles away, which is really far, and but I figured, and even for people like me who work in this stuff, it's almost unimaginably far away. But I recently came up with something that actually puts it into a sort of context. I was invited to a wedding in New Zealand, and New Zealand is 10,000 miles away from Washington, D.C. So going to the moon is like going to New Zealand and back 12 times from where I live. And I never really had an Earth-based context for that distance before. But anyway, so the moon is 250,000 miles away. Pluto is 3 billion miles away from the sun. And pretty soon after, we no longer measure things in terms of miles, because the numbers just get ridiculously large. So one common unit of measurement is called the astronomical unit. You generally use it when you're talking about when you're in one solar system. It's 98 million miles, or about 100 million miles, which is the average distance between the Earth and the sun. So then you have a nice unit you can use comfortably. So it's 30 AU out to Pluto, 3 billion. Now, that's obviously just the tiniest sliver of the tiniest corner of the universe. So we typically talk about light years. And forget all these easy numbers that have only 6 or 8 zeros. A light year is, it's so long I can't write it forwards, I have to write it backwards. A light year is, thousands, millions, billions, trillions. 6 trillion miles is 1 light year. 1,000 million, oh no, I left out some zeros. 6, okay, so this is 1 million, that's a billion, and that's a trillion. Yeah, okay, see, it's hard to even write it. 6 trillion miles is 1 light year. The closest star to the sun, this is the sun, closest star system to the sun, Alpha Centauri C, wow, I'm really messing up today, is 4.7 light years, which is about 25 trillion miles. Okay, and that's the closest star in our galaxy of 400 billion stars.
So
An almost unimaginable distance just to the nearest star, let alone other stars in the galaxy, let alone other galaxies. Now, someone was starting to ask a question. Let me just finish this thought, and then I want to hear it. The fastest object ever built by human hands, Voyager 2, my favorite spacecraft, has been in flight for 37 years.
what?
And it is traveling at, I forget how fast exactly, but it's gone 10 billion miles in 7 years. It would take 60,000 years at its current speed to get here, to get to the nearest star other than the sun. It's not pointed in that direction, but just to give you a sense of how far away the stars are with our technology. Now we go from engineering to physics. Physics, as in the universe as we understand it today, follows the rule that we talked about earlier. Push this way, you get something moves this way. That's how rockets work, how space propulsion works. Assuming this is it, it's going to be very hard to get to the stars and almost impossible to get to the galaxies, unless you're willing to wait billions of years. Now, the good thing is that every few hundred years or so, at least for the last 2,000 years, an extremely smart human being is born who comes along and says, oh, wait, all this physics that we know, everything we know about the universe, it's just a little piece of the real thing.
Amen.
So before Isaac Newton, let's go back even farther. Let's go back to the Greeks. The Earth is flat, right? Of course it's flat. Everyone knows it's flat. Actually, no. It turns out if you sail a ship over the horizon, first you see the bottom part disappear, then you see the middle part, then all you see is the mast, and then all you see is the sail. Well, how do you explain that? It's got to be a spherical ocean. So, okay, so the Earth isn't flat. So our worldview just expanded. 1,000 years later, Isaac Newton comes along and says, oh, there's three rules that actually govern everything, Newton's laws. Then 100 years will go by. Maxwell is born. Oh, it turns out there's the Maxwell's rules of electricity. Another 50 years later, Einstein is born. It turns out that matter and space and time are the same thing. It turns out that gravity is not what Newton thought. Where is he? Here's Newton, Maxwell, Einstein. Turns out that space is actually curved, and matter curves space, and that's why what Newton thought was an apple falling is actually an apple moving along a curved space-time that the Earth's mass is responsible for. So this is where we are now. And according to this guy, that's what we've got. And there's not going to be any shortcuts across the great distances between us and the stars. But if you go back long enough, you see that every one of these people is wrong eventually. I hope we live long enough to find out that Einstein was wrong, or at least that Einstein only saw part of the big picture. And if that day comes, then maybe we can get to other galaxies. But for now, we can't.
Would a light year take a year at the speed of light?
Yes, I'm so sorry. I should have said that first. A light year is by definition the distance that light travels in 1 year.
What proof do you have that the moon landing wasn't faked?
Well, you can Google. Is that a serious question? Do you actually think it was faked, or are you just curious? It's okay. I'm not attacking you. I'm curious if you actually think it's fake, or if you just wonder what the evidence is.
The evidence.
Okay. There's a lot of different things that can show you that the moon landing wasn't faked. First of all, you can see in photography taken from later space missions that there are actually six moonlanders sitting on the moon that you can see from space that correspond to the 6 times we landed on the moon. There's also a mirror that was placed on the moon. Here's the Earth. Here's the moon. mirror that was placed on the moon so that we can shine a laser at it and measure the distance from the Earth to the moon. That mirror is still there. Those are the logical reasons, the technical reasons. I will give you some other reasons as well. Let's think about what it would take. And by the way, what I'm about to say, I think, is applicable in life beyond just the moon. Let's think about what it would take for the moon landing to have been a hoax. 1957 or so, when NASA was formed. 1969 to 1972, when the landings happened. Okay. Soviet Union, USA. In the USA, there were 500,000 people working on this. In the Soviet Union, nobody knows exactly. I mean, maybe people there, in Russia do, but it was at least that many. You ever heard of a secret being kept by 500,000 people? Forever? No. For the moon landing to have been a hoax, every single one of these people would have to be in on it and agree to keep it secret forever, despite countless and unimaginable incentives to the contrary. And if it was a hoax, don't you think they might have pointed it out? No, they celebrated along with us when we landed on the moon in 1969. So that's the second reason why I think you can be confident it was not a hoax. The third reason is a bit more introspective, and it goes like this. Just because a person cannot imagine something does not mean it is true. I have seen from moon landing deniers the argument that it would be so unimaginably complicated that it must not have been done. And to me, that is a terribly sad failure of imagination. If you limit your imagination, if you limit your potential you currently know how to do, then you're going to be in middle school forever. I don't think you want that. So that's my answer to your question. I hope it was informative, because it's a really important one. Because there will soon be a day when there are no people alive who walked on the moon, and that will be a very sad day. And your question, as time goes on, will be more and more relevant, because there will be fewer and fewer people living who worked on it. So it's a very important question. Thank you for asking it.
So you mentioned before that space was curved, and like this is going into science fiction, but they say that you could fold, since space is curved, that either there could be a line between 2 points that are equally opposite from each other, or you could continue the curve and fold it, and that's basically where hyperspace and warp drives come from Star Trek. Yes. So it's all science fiction.
Yes.
Is there any reality to that at all, as far as you know from physics? I know there's been a lot of new papers written on it.
So this is a subject of very significant interest to me, because I would love almost nothing more than for some of that to be real. Let me walk you and everyone there through some of what these ideas might mean and what they maybe mean in reality. So what's the shortest distance between 2 points? Somebody?
Straight line.
Wrong. If you're on a planet, the shortest distance between 2 points on the surface is a curve, because the planet is curved. If you're a two-dimensional bug, then yes, the shortest distance between 2 points is a line. Now, imagine you're an ant, and this is a piece of paper. If you're an ant and you want to walk from here to here, you have to cross this distance, right? Well, what if you could pinch the paper and you could bring this point closer to this point? Then you've decreased the distance you have to walk. That is a 2 into 3 dimensional idea for what we would love to be real about the actual universe. Because right now, you want to go from the Earth to the moon, you have to cross 250,000 miles of space. But what if you could pinch the 3-dimensional world like we pinch this paper for the ant? Wouldn't that be something? That is the idea behind warp drives and stuff like that. I believe that most traditionally trained physicists would say that is not possible. And I don't have any real data to argue with that, which is why I hope that, as I showed you earlier, that someone eventually shows that Einstein was only seeing part of the big picture, and that maybe some of that is possible. So that's my answer to that question. There's a constant tension. There's a constant tension between in the scientific world, and there has been for 5,000 years, about the knowledge and the understanding of the current day being it. That's it. Everybody knows the Earth is flat. Don't bother looking into it. And every couple of hundred years, somebody smart enough and determined enough comes along and shows that that's not the case. I don't know if this will turn out to be the case or whether Einstein saw everything. But even now, we know that Einstein's approach and quantum physics are not compatible. We know that. We know there's at least something bigger than that out there that we haven't studied. So whether that something will allow us to pinch space and move across three-dimensional space in less time than it would take to go directly from point to point, I don't know. But I hope so. And I'm going to read all the same papers too when they come out, because I really want it to be real.
How fast exactly is NASA's internet speed?
Oh, that's a good question. So when I was at JPL, the internet speed was a gigabit download and upload, which is pretty awesome. But let me tell you a funny story about that. There's a gigantic experiment called the Large Hadron Collider. It's basically a 16-mile diameter tube in France that sends protons at near the speed of light and smashes them into things to break apart the fundamental particles of the universe. As you might imagine, this thing generates a huge amount of data. And for the first some number of years of its operation, it generates, let's say, this amount of data. This amount of data was actually put onto thousands of hard drives and put onto airplanes and trucks to take the data from France to Los Angeles for analysis at the California Institute of Technology. They actually flew hard drives worth of data in airplanes full of hard drives across the world. Now it goes over the internet. But I just want you to imagine a FedEx truck or something full of hard drives from one research institution to another.
That's interesting.
It's ridiculous, yeah. But there was no other way. I mean, another great story is there's a science fiction author named Gentry Lee and Arthur C. Clarke, and they wrote a book together, a really great book. And one of them lived in Los Angeles, and one of them lived in Sri Lanka. And so they wrote this book in the 80s, and they sent back and forth giant stacks of paper around the world. And it was so bad that in Sri Lanka, the postal workers went on strike because they were tired of carrying 100 pounds of paper up the mountain to this guy's house. And they finally finished the book, and then the next week, the fax machine was invented.
So we're not to limit our imagination.
Yeah, you just can't wait for the next technology to make what you're doing.
Yeah.
And by the way, at NASA centers, the printer doesn't work half the time, and the phones don't work. It's all the same stuff you deal with. It takes 3 or 4 people to change the ink cartridge. Nobody knows where the paper is. It's just like any other place.
Do you believe in aliens or other human forms?
I'm so glad you asked that. I don't. Before we answer that question, I don't think "believe" is the right word to use. At the risk of getting into certain areas of discussion that are not appropriate for public school, I don't think "belief" is the right word. Belief implies a lack of evidence, and to me at least. And I think there is a lot of evidence for a high probability of extraterrestrial life, and I will share that evidence with you. We live on planet Earth around. Okay, so there's 9 planets in our solar system. There's 400 billion planets in our galaxy. 400 billion. That's 400,000. That's 400 million. That's 400 billion. I'm gonna write 9. 9. Okay. There's hundreds of billions of galaxies in the sky. So I'm going to just say another 400 billion, although the number is probably higher.
And that's galaxies?
Galaxies, yes. So if you multiply that together, that is...
That's a lot of zeros.
How many zeros? That's 24 zeros times 8 times 9. That's like a lot. That's something. If you assume that there are 9 planets around every star, that's a ludicrously high number of planets. And it turns out that when we actually look at other stars to find other planets, we find them. And we find most stars have some planets, and some stars have even more than 9. So it's a fair bet that, I have a great graphic for you. So here is the center of the galaxy. These are the galaxy spiral arms. I'm guessing that where you live, you don't have a lot of light pollution, so you can probably see the Milky Way galaxy at night sometimes. So we're out here somewhere. We're actually pretty far from where the action is. And when we built the Spitzer Space Telescope and the Kepler Space Telescope to look at the nearby stars, we are only really able to see that much.
Oh, wow.
And we've found thousands of stars with planets around them. And that's just in galaxy number 1. Oh, wait, that's planets, sorry. That's just in galaxy number 1. Okay? And, as you saw last week, a nearby star that's about 40 light years away has 7 planets the size of Earth. Okay? You multiply all of these numbers together, you literally think about this carefully, and you tell me, does it really seem like this is the only place in the entire universe where life could have emerged? No.
Absolutely.
Now, to further raise the possibility, let's talk about places in our solar system where there might be life. Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto.
Pluto!
Obviously, Earth has life. Mars. We now know that Mars has all of the necessary chemicals for life. Maybe. We know that Jupiter, one of its moons, has a deep underground ocean that has more life in it, more water in it than all of Earth. And it has the same chemicals that we need, that we know on Earth at least, become life. Saturn, there are 2 moons, Enceladus and Titan, where there is at least the chemical possibility of life. That's 4 places in one solar system, and we're not even done looking yet. Think about the big numbers before. I think it's an absolute certainty that at some point in the universe, somewhere else, there was at least some kind of life. Now here's the problem, and here's where it gets depressing. So all this was really uplifting, but here's the depressing part. The history of the universe, 13 billion years, 13.7 billion years. That's a 17, it's not 13. 13.7 billion years. The Big Bang, today. How much space on this bar do you think human life covers?
What do you think of Evan?
Like, not even that much.
Right, like less than the width of, less than the minimum diameter line I can draw with the pen. Much less. We know that the early stars were probably too hot to support planets with life, so that wipes out the entire first half of the universe. By the way, most stars that are around now are second generation stars, at least.
Wow.
Our sun formed about 5 billion years ago, which was about 8 billion years after the Big Bang. So let's say that's about here. 8 years after Big Bang. We'll just call it AB instead of AD. 8 billion years AE. 8 billion years A. So now this is just the Earth. The Earth has only been capable of supporting life for about 2 billion years. That's 10 billion years AB. For most of that time, the life was microbial. Then we had then we had cells, plants, and dinosaurs and stuff.
Oh, yeah.
So here's the thing. There's a lot of different theories about this. One way to look at this is to say, well, it's possible that if there ever was life, now is about the right time. And if we look at our own star and planet, that's what we see. But we don't know about this for sure. This is just based on what we understand life to look at. So if you start this over again, and you wipe out the first few 100 million years because the universe was a hot mess then, literally. Here's the thing. If there are other human-like intelligences out there, they could have popped up here and disappeared there. They could have popped up here, lasted 1 billion years, and disappeared there. And of course, this is distributed over a vast amount of space. Now, unfortunately, the odds of us popping up here and someone else popping up here and them being close enough to ever possibly interact with, sadly, that probability is about 0. As far as we know. And so I fear we may never know what has come before or what may come after us. Now, that doesn't mean we might not find evidence of life. For example, we could find fossils on Mars or something, and that would be amazing because that would basically expand the list of planets that could support life from 1 to infinity, because we would know there's at least 2 places, which is a lot more than knowing there's 1. So the universe could be crawling with intelligent species, but they could be so far apart in space and time that they will never meet. And this gets to a philosophical and scientific debate that is largely pointless but interesting. So while I think it's almost guaranteed that we will discover evidence of life in our own solar system in our lifetimes somewhere else, I think it's almost impossible that we will ever encounter intelligent life, as much as I want to. And I can't argue myself out of that conclusion, unfortunately.
Jeff, our bell is going to ring in less than a minute, but this has been an honor. It's been a gift, and we give him a thank you. You have had fantastic answers for us, and I know you've only just spurred us on to want to know more. So
sure, well, email me on the platform. We can do this again.
Yes. Oh, that would be fantastic. Yeah.
Cool. All right, well, thank you. Take care.
Thank you. Have a great day.